Welcome to HVAC Talk with Huff. I'm Huff. Today, I'd like to address the issue of heat pump heating performance, specifically in delivered BTUs. Have you ever gotten a service call or call from your customer saying that they're not convinced, or they're not happy with their heat pump and how it's operating, and they paid a lot of money for this brand new heat pump system, and they feel it should be performing better? And so today, I want to address how to instill confidence in our consumers about their heat pump operation, or the flip side of that, how to determine just what the heat pump is delivering at BTUs and whether that is correct, whether it's performing up to standard. And so we want to talk about how to actually go about this. And I'm going to share a three-step process that I have used, that I used in the field many years as an OEM tech rep, to be able to address these issues. And so let me talk about what those service calls look like. Maybe the call comes in that the homeowner's complaining that the heat pump runs continuously, that it's always running when it gets cold out. I've had a lot of technicians go out there and they say, well, I checked the system over, I couldn't find any problems. Of course, then I asked for data, and, the service ticket looks like, check pressures and temperatures, got a good split, everything's fine. The homeowner is going crazy, those kind of things, right? And the fact is that we're dealing with physics, we're dealing with designs, we're dealing with equipment that is designed to achieve certain results. And because it's physics, it's science, and those kind of answers aren't data driven. And the only way we're going to instill confidence in customers is to actually capitalize on our understanding of the science and give them data that actually shows that the system is performing. Or the data will uncover that the system's not performing so that we can address it. Either way, we must go about this in the right manner. Maybe the complaint comes in that it's not keeping up. The system's not keeping up and not maintaining a set point in reasonable conditions. Where reasonable conditions means, we're above the outdoor design temperature or something like that. So, of course, there could be many reasons for this. I've seen issues where people didn't connect the aux heater, and so the system wasn't keeping up when it got really cold out, because the heat pump alone was not enough to cover the load. Right? I've seen thermostat wiring issues. I've also seen issues that were just not sized correctly, things like that. And even though that may be the case, our approach to determine this is going to be the same. In other words, I approach it the same way regardless. Now, before you ask the question, what about load calculation? Well, we should be doing a load calculation on every job. However, a lot of times I was called out to jobs where a load calculation had not been done. A lot of times they replaced the equipment with the same size that was in their previous. And we can have a different conversation about that. I'm all about doing load calculations. However, many of the times I had to go out on jobs I didn't have that information, but that did not change my approach, because my approach has to start with what is the system doing. And I mean, when I say it's doing, what do we actually measure it as far as delivered capacity, and what is the system capable of delivering? And then once we determine that, then we can branch out and talk about whether the system is sized correctly or things like that. Another complaint would be that using too much auxiliary heat, electric bill is too high, right? Some other things that also play into this is sometimes people will lock out their aux heat, whether it's electric heat or even if it's dual fuel, they'll lock out their aux heat at a temperature that is just kind of arbitrary. They chose that temperature, and that may or may not be the right temperature to lock out that aux heat. They may be locking it out lower than what the system is capable of handling due to the actual load of the space. And so, again, we're not going to get into big and low calculations. What we want to really center in on today is how can we determine what the heat pump is doing and what it should be doing, so that then we can move to the next issue, if you will, or be able to actually instill confidence in the customer that the system is working correctly. Either way, we need to figure this out. We need to find out what it's doing, what it should be doing. And so I'm going to share with you this three-step process, if you will. So step number one, measure airflow. And I'm no guesstimates. Why do we want to measure airflow? Well, first off, we can't determine our delivered capacity without measuring airflow. Airflow is part of the equation. Our BTUs per hour is the formula for that is 1.08 multiplied by the cubic feet per minute of airflow multiplied by the delta T. Now, again, we're measuring the heat pump operating without the help of any aux heat. So we're just running the heat pump right now, and we're measuring what the heat pump itself is doing to find out, either why the system's running a lot, whether it's running correctly, right? And so to be able to do that, we have to measure airflow first. Can't be any guesstimates, can't be anything like that. Now, how do we do that? Well, my number one choice would be the TrueFlow Grid. It's an amazing, it's an amazing setup that measures airflow, and it does it very accurately. It's a wonderful tool. It's not cheap, but man, it sure does get the job done, and it leaves you without question. Another thing that sometimes people overlook is if you have an ECM blower that is a constant CFM. Remember, ECM blowers kind of come in what I like to say two flavors. You have your constant CFM, and these are the variable speed blowers where you set the CFM. Whether it's through a communicating thermostat or whether it's dip switches on the board, things like that. And then that blower is going to ramp up against the static to deliver that airflow. Now, the second flavor of ECM blowers are what we call constant torque. And as the static is increased, that blower will slow down, kind of like a PSC motor, but not near as bad. But that motor, you can't use this on. But if it is a ECM constant CFM motor, then you can actually go off those airflow settings, whether it be in that communicating thermostat or whether it be on the settings on that board. Some boards will even give you blinking lights to deliver, how many 100 CFM they're delivering. And so that is a fairly accurate method to use. According to the factories that I had worked for. The heat rise method, and this is specifically when you have an air handler with a strip heater. You can do heat rise method on a gas furnace, but it's not near as accurate because we would have to know the actual firing rate and then the net BTUs to be able to use that information. Where with the heat rise method, when you have an air handler with a strip heater, you're able to measure the voltage and the amp draw at the heater, and then also the temperature rise across that heater. And we can use that information to be able to determine airflow. I actually called Jim Bergman about doing this video and just wanted to get his take on that. And he said absolutely that the heat rise method is an accurate way. Now, the one thing that's important is, and he made note of this when we were talking, is that, just make sure you tell them, Huff, that, that when you measure that supply air temperature, it's got to be out of sight of that heater. So any of you who are MeasureQuick users, that we typically place the air probe in the first outlet downstream from the equipment, right? So that very first outlet coming off that duct system. So that's just an important part. Some people will say, hey, I can use static pressure with my fan tables. Well, that's actually the least desirable. Now, I know what you're thinking. Well, aren't we telling people that they should be checking static pressure on every job? Absolutely. We should, every service call, we should measure static pressure. In that way, we know what how restrictive the duct system is. However, when you got a really turbulent duct system, I have seen, especially when you got like short supply plenums with multiple taps coming out, and we don't have a good, straight section for laminar flow of air, then you can find that turbulence will cause issues in that airstream, and you may put that static probe in the center of that supply plenum and then maybe move it 2 inches to the left or 2 inches to the right and get a totally different reading. And so that's why we don't like to use this for this measuring airflow for this performance. So step one has to be measuring airflow. Step two, we measure the delivered capacity. Now, there are other ways to do this. I happen to use MeasureQuick because honestly, it's effective, it's accurate, and honestly, I guess, hey, it's easy, right? If you have the Bluetooth tools, especially where it's going to read your tools, once you understand and know how to set it up, you can do this fairly quickly. Now, on this kind of test, I'll be honest with you, I'm going to be using the heat pump non-evasive check. The reason I'm doing that is because right now I'm just trying to determine the capacity of the system with the heat pump running without any help of aux heat. And I want to see what the delivered capacity is of the heat pump as it's running. Now, I'm not going to be checking pressures. I'm not checking the charge at this point. I'm trying to determine how the system is running at this moment in time. Now, you may find that as you go through this process, maybe measuring airflow may uncover a problem. Now, if it does, I would implore you to go through this process first. And if you uncover an airflow problem in this process, go ahead and go through the process of measuring the delivered capacity and checking that against the OEM charts that we're going to do, and then make the correction and then go back and do it again. Why would I do that? Well, if you think about test in, test out. If I measure the capacity now as it stands the way it is when I got there, and then I make an improvement and then I test again, I'm able to prove my work. I'm able to show that the amount of BTUs I measured when I got here, and then the amount of BTUs I measured once I made the correction, and then I can just do some quick math and I can show you the percentage of change. You can say, you know what, I increased the delivered BTU capacity by X percent, right? And so when you uncover a problem, go ahead and still measure the capacity and take that information and then make the correction. That way you're able to show. But because if you go there and you uncover something and then you fix that first, you don't know how much change you actually that you were able to get out of that system and how much improvement. And being able to prove our work mathematically is key to helping customers understand and have confidence in your serviceability. Now, when you're using MeasureQuick, you want to make sure, again, you want to use an outdoor air probe. In other words, don't be using WeatherBug, things like that. You actually want to be able to measure the outdoor air temperature right at or near the outdoor unit. Why? Well, if you use WeatherBug in my area, the weather station is about 14 miles away. And a lot of times my house can be 4, 5, 6 degrees colder than where it is where that weather station is, just because of where I'm located up in the side of this mountain. So, you want to actual measured outdoor air temperature. You want to measure that supply temperature at the closest register, just like we talked about. And then you're going to take the return temperature at the largest return grill. Now, I know I'm not covering MeasureQuick's non-invasive test. There's already videos out there. Matter of fact, Tim DeStasio, I think, released one just last week. That was done really well. I may do one later, but for now, I'm just talking about the methodology we use to either uncover a problem or solidify the confidence for the end user and their system. Now, I will tell you this: if that indoor unit is in any area that's unconditioned, such as an attic or an unconditioned crawl space, one of the things that I like to do is I like to actually take a measurement, not only at the return grill, have an air probe at the return grill like we would normally do, but I also like to take another return temperature measurement at the air handler and compare and see if there's any difference between the temperature at the return grill and the temperature at the air handler itself. Why would I do that? Well, what if there is some air leakage and I'm sucking in attic air or sucking in crawl space air? Think about what that is going to do to my system. Now, if I uncover that and I find that problem, guess what I'm going to do? I'm still going to measure that capacity the way the system stands, and then seal that up and then retest again. And that way, again, I can show the percentage of improvement I made on this system. Right, step 1, measure the airflow, no guesstimates. Step 2, measure the delivered capacity. Now, if you're using MeasureQuick, when you're going through your indoor information, like in your gauge view, and you go to indoor, then when you do that, you can go in and you can actually enter in the measured airflow. And that way it's going to use that number that you measured in calculating the delivered capacity. So you want to make sure that you do that. Then step 3, this is the part that I don't see other people talking about. And this is what I learned working for the OEMs for those years, right? So we measured the airflow. We now measured the delivered capacity using those airflow numbers that we took. Now we're going to compare that to what the OEM says the system should be doing. In other words, we're not guessing anymore. This data gives you the needed context for what the equipment is designed to achieve. And it's one thing to say, well, a 2-ton unit should deliver, 24,000 BTUs, okay, down to what temperature? And so I find that every tech has an idea of how many BTUs that should be, and most of them aren't right. And not to mention that it will vary from manufacturer to manufacturer to some degree. Secondly, what about the type of equipment? It's one thing to have a single stage 14 SEER heat pump, but what if we have a 17 SEER variable speed heat pump like the one I have in my house, right? So the only way to truly verify the performance is to take the measured capacity and compare it to what the manufacturer says it should be able to do. Without this data, we are just simply guessing. We're simply guessing. And so with this data, we're actually able to rule out, any type of equipment issues. Or we will uncover an equipment issue. Now I just realized my picture is blocking part of this slide, and so is my little Huff's Cool Bus in the right-hand corner. And so let me take myself out of the picture here. And unfortunately, I covered up that T by accident, but you get the idea. So we measure airflow, We measure the capacity using that measured airflow number so that we know it's accurate. And now we're going to compare it to what the manufacturer says it should be able to do. Now, I know what you're thinking. Well, I'm out in the field, Huff. And when you was an OEM rep, you actually had access to all that. Absolutely. But I'm getting ready to show you some performance charts on equipment for manufacturers I never worked for. And I'll be honest with you, now that I'm doing the kind of work I'm doing now, I don't have access to that stuff. And so everything I'm going to show you, I found either using Google or I found using Chat GPT, and you can do the same thing right on the job site. Now, if you don't have the ability to do that or struggle in that, then most manufacturers, if you call their support line, even to the supply house, and you tell them, hey, I just need the detailed heating capacities on this heat pump I'm working on, most of the time they'll be able to send it to you. And most of the time, even counter folks working the counter that may not be technical, but they have access to that information. So there are ways to get this. We have to start being a little more responsible. So this is actually Goodman's heating chart. And I'm actually going to blow this up a little bit so it's easier to see. Now, this is a 2-ton Goodman. This is a GSZ 14, which is a 14 SEER Goodman. 25 is a 2-ton. They have a 24 and a 25. The 25 is made for the longer line set. So it's more of a long line that's used in like multifamilies. And so notice here that it says the calculations are based on nominal CFM and 70-degree indoor drywall. Now, just for sake of brevity here, I didn't bring in the cooling capacities, but when you find this document, and I'll tell you what I typed in Goodman GSZ 14 heating capacities, or sometimes you may put in submittal data. So you got different manufacturers call it different things. So Carrier calls their capacities are listed in what they call their product data. York is listed in what they're called their technical guide. And so you just kind of got to figure out, what your, the wording to get the right results. And you may have to try a few times, but again, it's not too hard to find. Now, so nominal CFM in this particular unit, I happen to know, is 435 CFM a ton, not 400. And in the cooling capacities, when you get to that section, you would see that. So let's look at this chart. So across the top, it starts at 65, and you see that the temperature just keeps going down. And so let's look here at 30 degrees. So at 30-degree outdoor air temperature, again, return air temperature, this is based on 70 degrees and at 435 CFM per ton. And based on that information, this unit should be able to deliver 16,570 BTUs. Remember, this is MBH, so we have to multiply by 1,000. So that's 16,570 BTUs. And so look, right there, the manufacturer is telling us what the equipment should be able to do. And then the next one is 25 degrees. And at 25 degrees, it'll be 15,360. So Huff, what do we do if our temperature is in between that? Well, we use the process of what's called interpolation. And so interpolation is the process of estimating unknown values that fall between known data points. Essentially, it's filling in the gaps by finding a value that fits a pattern or a trend in the existing data, like finding the halfway point on a graph. So in West Virginia, we call this splitting the difference. So we're going to look at the capacity above the temperature and below the temperature, and we're going to kind of split the difference in the middle and find out kind of what makes sense. Now, typically manufacturers will tell you that, as long as you're within 10% of what the product data says the system can do, that they consider that, acceptable. So now that you'll find also, and again, I'm just giving you the down and dirty quick on this, but once you start looking through these kind of documents, you'll find that there'll also be correction factors where, okay, so if you have a CFM that is below this or above this, they may have a correction factor where they'll tell you to multiply this BTUs by, a 0.98 or 1.03, depending on whether the airflow is higher or lower. And so you have to take a moment, you have to read through the documents, but imagine you being an end user and you're questioning whether the system's running correctly, and a technician comes out and says, well, it looks like it's running fine to me. They're not necessarily going to be happy with that. But what if the technician says, okay, I have first off measured your airflow, and then I used that information and was able to compute your delivered capacity of the system right now as it's running. And so now that I know how many BTUs the system is moving, now let me show you what the manufacturer says it should be doing. And being able to show them on paper that the system's performing, or Maybe you uncover that the system's not performing, and at least you can address it then. Either way, it's going to help you either instill confidence, or it's going to help you understand what needs to be corrected on the system. So let's look at another manufacturer. This is Carriers. This is a 25 HPB 6, which is a 16 SEER. And we see that both the 18, which is a 1.5 tons, and the 2 ton. Now on this one, they call out the actual matching air handler. And with Carriers product data, I can tell you that if you use an air handler different than this, they're going to give you a correction factor. So let's blow this up a little bit so we can see it a little bit better. So this one's laid out slightly different. First off, we still have outdoor air temperature across the top, but this one goes from low temperature and it increases to the right, where earlier we were high temperature and decreasing to the right. But we have our outdoor temperature. And so let's look at this one for 17 degrees. And then we come over here to on the left in this vertical column, and we have entering dry bulb temperature. So we have 65, 70, and 75. So let's go with 70. And then we still yet have another selection to look at. Now we have also vertically beside that CFM. And so Carrier gives you 3 choices: 545 CFM, 600 CFM, or 675 CFM. Now, let's say 600. So how would I use this chart? I'm going to carry 600 over here until I get to that 17 degrees. And the capacity of that system as it's running is 10.80, which would be 10,000. Again, this is MBTUH. 10,800 BTUs when that system is running. Now, Carrier does this funny thing where they show you integrated capacity. What integrated capacity does is over that hour of time, it takes into account the effects of defrost. When I go to defrost, I'm going to absorb heat from the inside and put it back outside to defrost the coil. And so that does have, a little bit of an effect on the overall delivered capacity over that course of time. But when we're measuring right now in real time, we're going to actually use this column right here. And so you can see how this chart works, right? So we locate our outdoor temperature, we locate our indoor dry bulb and the CFM, and then we're able to plot this out. Now, here we go from 17, then it goes up to 27. So that's a 10-degree gap. But the difference is only, about 3,000 BTUs in between that 10 degrees. And so I can fairly easily interpolate in between those two, depending on if I'm in the middle of that, or maybe I'm at 23 degrees. It's not hard to actually take the amount of degrees in between these two columns and the amount of BTUs between them and come up with an easy way to determine about what those BTUs should be. But again, hopefully you see the benefit of this. Now, this is a train performance table here. This is a Ford TWR4, which is a 14 SEER 2-ton unit that you see right here. And it shows you what the matching air handler is and the CFM. Now, down here below, it shows correction factors for other combinations. So if you're using a different air handler, it gives you a multiplier. Now let's blow this up a little bit. And so we have our outdoor temperature on a vertical line here. And then as we go across the top, we have indoor dry bulb. So we have 70, 75, and 80. And we go down, let's say at 32 degrees, at 70 degree entering air, 15.8 would be 15,800 BTUs. Now notice below that, we have correction factors for airflow, low and high. So instead of 800 CFM, if we're at 700 CFM, we're actually going to adjust that capacity by multiplying it by 0.98. If we're at 900 CFM, we would multiply it by 1.01. So now you can see these correction factors. So let me wrap this up by showing you what it looks like when you do this. This is actually my system. Don't worry about all that math at the bottom. This is a slide I use for the US Heat Pump Summit, just to kind of show how the COP is actually calculated, but we don't worry about that right now. So outdoor air temperature at the time of this test was 16 degrees. Now, I actually entered this in because I had a digital thermometer right out by my outdoor unit, and I was able to see it through my window. And so I didn't want to go out at 16 degrees to put an air probe out there, but I did take an actual measurement with a very accurate digital thermometer that was outside. And so I keyed that in. And then I actually when I did non-invasive, I was actually taking line temperatures as well. So I knew kind of see what was going on. But here's my air probes. And you can see that I was using Fieldpiece air probes. You can tell by the little icons here. And so again, when you're doing non-invasive, not only do I want to take temperatures, I do also like taking electrical data, because it's not only going to give us delivered capacity, but it'll actually calculate the efficiency, system efficiency as well. And so look at how impressive this information is on this non-invasive report. And you can see right at the top here, non-invasive heat pump heating snapshot. It was taken January 20th, 2025 at 6:59 in the morning. Now, I did this before the sun come out because I wanted to see exactly what my system was doing, because I was trying to really determine my balance point in a real world application. Now, you can see here that my system is delivering 17,620 BTUs, and this is a 2-ton 17 SEER inverter driven heat pump. You can see my temperature split was 20.6. Now, just to make sure, because I know people will question this, if you see this normalized here in Measure Quick and it says 0.8 tons at 9,580, that is based on just a generic 14 SEER heat pump. And so this is why we want to make sure we measure against the actual and compare against the actual OEM's data and not using normalized in the heat mode. Now, in the cooling, when you're setting up your cooling profile in Measure Quick, you can put the extended performance tables into Measure Quick on the cooling side, but not the heating, because it just varies so much. And so this is why I'm doing this video. This is why we're talking about literally going back to the OEM's documents. So I'm delivering 17,620 BTUs to my house. Now, my return temperature is 68.5. My thermostat was reading 70. They're a little bit distance between each other. And I also found out why it's reading 68.5. I did have a little bit of air leakage coming in from where this mechanical closet was, and we got that figured out. But, still yet this delivered capacity is correct. Now, I'm going to show you what the actual data says from York that says what my system should be doing. This is a York side discharge inverter heat pump, and we're going to look and see what the data says that I should be delivering. And so at the top we have indoor CFM, and so we got 600, 800, and 1,000. And so my BTUs was actually 892, if I remember correct. Let me go ahead and double check that. 792. Yep. 792. And so right here we have the capacity at 17 degrees outside, at 70 degree entering dry bulb air. And based on those conditions, now my outdoor temperature was 16 and my return temperature was a little under 69. And so it's still yet very comparable. But at that temperature here that we see on this chart, it says 17.2, which is 17,200. And notice the COP, it also gives a COP in this column here, says it should be 2.21. And so that's what the manufacturer says the equipment's capable of under those conditions. What is my system doing? It's outperforming it by a couple hundred BTUs. And again, we're going to make sure being within 10% is what the OEMs consider as acceptable. And my COP is 2.22. So I'm actually outperforming what the manufacturer says that system can do. And before you start giving all the comments, I do have very low static. My ductwork is sized really well, but I got to tell you, it's not sealed. And so my system can do better, and it will do better because I'm getting ready to seal all my duct system up. And so right now I do have duct leakage, and I haven't measured it yet, but I know it's because I've been under there. It's in a crawl space. And so we will be measuring the duct leakage, sealing it, and then measuring it again. And I expect these numbers to actually improve. So think about that. So hopefully you see, measuring airflow, then measuring delivered capacity using those airflow numbers, and then comparing that to what the manufacturer says the system's supposed to be doing or can do, can either A, satisfy the end user, or B, uncover a problem that will actually send you to, go find out what's happening with the system, or C, it may be that the delivered capacity matches the chart, but then you may have to go deeper. Maybe that system is not sized correctly for that home, or maybe you do have a massive duct leakage somewhere, and you're not delivering that heat actually into the space or something like that. But for me, it always started with verifying the equipment operation first and then working my way. This process has served me well over many years. It's very simple, but it works. And I'm thankful for the mentors that helped me out over the years that kind of helped guide me in this and really helped me see, that first off, you're not measuring, you're guessing. And then when you do measure, you got to compare it to something. What should it be, right? And so these are the things that we need to be doing that can actually help us either instill confidence or uncover a problem. Hope this has helped you. The next time we do a video, we'll actually cover what to do when the capacity is not within that 10%, specifically when it's low. What do we do when that capacity is low, and how do we address that? So I appreciate you taking the time to listen to the video. Hope it helps. If you have any questions, please, I'll put my email address in the description. Hit me up. I'd love to talk about it. Right? Maybe we can even make a video together. We can talk these things out and talk about what it looks like on the job site. And I got a bunch of stories that I would love to tell about this. Right? So even recently, some ones we ran into where we had plenums that were leaking in the attic and causing performance problems, and it simply was because we were taking in attic air. So these kind of things happen. So hopefully, we'll see you on the next one. Appreciate.